For decades, the relational database has served as the absolute gold standard for storing information. It is built on a foundation of total certainty. That certainty comes from a set of strict mathematical rules known as ACID properties. These guarantee that every transaction, like transferring money between two bank accounts, is perfectly consistent. If even a tiny fraction of the operation fails, the entire transaction is canceled, ensuring the database never holds a half-finished record. To handle more traffic, these traditional databases relied on vertical scaling. When you ran out of capacity, you simply bought a bigger, more expensive server, cramming more CPU and RAM into a single machine. This reliance on a single piece of hardware has a hard physical limit. As global e-commerce and millions of concurrent users hit the web, the rigid perfection of those ACID rules created a massive performance bottleneck. The solution was horizontal scalability. Instead of buying $1 million supercomputer, engineers started splitting massive datasets across clusters of cheaper commodity servers, a process called sharding. Distributing data across a network introduced a famous engineering adage: you have to pick any two. The rule stated that you could have consistency, availability, or partition tolerance, but never all three at once. Look at this network grid. If a connection between two servers goes down, the system is forced to choose. You either freeze the entire database to prevent bad data from being written, sacrificing availability, or you keep the system running and risk serving outdated information, sacrificing consistency. For a long time, developers accepted this rigid trade-off as a law of computer science physics, but we need to ask if it is a permanent limitation of the hardware or just an outdated assumption. Applying the strict single-machine rules of older databases to modern sprawling networks created a false binary. This mentality choked the scalability of early web applications. To break past that bottleneck, the NoSQL movement emerged. It rejected the rigid tables of the past, embracing a new philosophical model called BASE, basically available, soft state, and eventual consistency. The BASE model removes the requirement that every piece of data must be perfectly synced across the globe at the exact same millisecond. It allows the system state to remain fluid, trusting that all servers will eventually catch up and agree on the correct data. Apache Cassandra represents a major shift in this philosophy, a wide-column, masterless peer-to-peer database built specifically to prioritize continuous uptime. Cassandra uses a masterless peer-to-peer architecture. Notice this circular ring. Every server node plays an identical role. Because every node is equal, there is no single point of failure. If one server crashes, the system reroutes data packets to surviving nodes, keeping the database online. Of course, that raises a challenge. When handling financial ledgers or medical records, you cannot rely on eventual accuracy for the most critical operations. Cassandra introduces tunable consistency, turning the choice between speed and accuracy into an adjustable dial. For IoT streams needing maximum speed, set it to consistency 1, writing to a single node. For financial checkouts, consistency quorum requires a majority vote before approval. Instead of forcing a permanent system-wide compromise, this architecture negotiates the balance between speed and accuracy on a granular, query-by-query basis. While tunable dials are powerful, they aren't the only way to manage data across a network. Other NoSQL databases tackle this spectrum using different structural blueprints. MongoDB, a document-oriented database, manages distributed data using a single master with replica sets architecture. In this hierarchy, MongoDB prioritizes strong consistency. All new writes are routed directly to one central primary node. That primary then copies the new data down to smaller secondary nodes, which act as automated backups. Modern database development tools provide dynamic architectural options that adapt to the specific needs of the network. The pick any two rule functioned as an architectural boundary for older technology, rather than an ironclad law of computer science. Today, engineers define their exact requirements for speed and accuracy at the very millisecond a query executes. We are now operating in a landscape built on fluid distributed systems and adjustable metrics, leaving those rigid binary constraints behind. Modern database engineering achieved global scale by treating perfection as a negotiable parameter.